Hello, it's Scott Manley here. Over the last 2 weeks, I have been basically transfixed by the Coast Guard's inquiry into the Titan submersible loss. This submersible imploded near instantaneously over 3 kilometers below the ocean's surface. And a lot of people are deeply interested in how this actually happened. I mean, beyond all the press-worthy stories about Stockton Rush, his cost-cutting, and his dismissal of experts who actually knew what they were talking about. But I don't want to focus on that kind of drama. That's the easy mode. I want to focus on the technical stuff. And there were a number of experts in marine engineering who testified, and mostly I want to focus on the presentation by Donald Kramer of the NTSB. Now, the NTSB are in parallel performing their own analysis. And what was presented at the hearing was a bunch of analysis of imagery of the debris on the seafloor, recovered debris, and detailed material tests performed on recovered portions of the carbon fiber hull. This is not the NTSB's final report. That will come at some later point, but this gives us a lot of information about what was going on at the microscopic level inside this carbon fiber hull. So, as you probably know by now, OceanGate's Titan submersible used titanium end caps, which were spheres, clamped onto a barrel-shaped section made of 5 inches of carbon fiber composite. The reason why OceanGate wanted to use carbon fiber composite for their pressure vessel was they wanted their submersible to be as light as possible. Steel was better understood, would be relatively easy to fabricate, but they would need to have a type of foam, syntactic foam, which would help the vessel float to the surface. That would make the whole submersible much heavier, and in turn would mean that the support ship would have to be heavier. And if your entire business model revolves around selling tickets to dive into the ocean, you want support costs for every trip to be as low as possible. And in the early 1/3 scale models that they built and tested, they actually tried building carbon fiber end caps, the dome shapes, but those actually were the failure points in their early tests. So they instead decided to go with these titanium end caps, which would be a bit more expensive, but they were known to be more reliable. Fabricating these spheres for deep-sea human-rated submersibles was well understood because they tend to use spherical pressure vessels, the reason being that a sphere is an ideal shape for a pressure vessel, and what the OceanGate design has is 2 hemispheres with a barrel-shaped section in between. If you do the simple pressure vessel math, then the stress that is placed on a sphere is half that is placed on a cylinder. And the simple way to think about this is a curved pressure vessel is a bit like an arch on a bridge. The load is being spread out sideways along the legs of the arch. Now, in a cylinder, that's a bit like a bridge arch. Well, a sphere has the arch going in 2 dimensions. Therefore, it's distributing the force in 2 dimensions. Therefore, the force, half as much force is being presented through the material, right? And I should just say that while I am familiar with engineering terms, I'm probably going to misuse the terms strain, stress, load. So just bear with me. I'm trying to make this understandable. So anyway, as it happens, titanium is one of the materials which is actually allowed by the American Bureau of Shipping to build pressure hulls for human-rated submersibles. You can also use steel, aluminium, stainless steel, even acrylic plastic is allowed for a pressure hull. Carbon fiber composites are not allowed. And of course, there's a bunch of armchair engineers out there saying, well, of course, carbon fiber composites, it's all about the fiber strength. That means they are great under tension. Those fibers redistribute the load throughout the material, but under compression, those fibers don't work in the same way. And so many people are very cagey about the idea of using a carbon fiber pressure hull. But marine engineer Bart Kemper, who also testified, made it clear that really none of these problems are necessarily showstoppers, and the real reason it's not used or not approved is because it hasn't been tested sufficiently to solve these problems. He actually presented a table showing composite submersibles, including China's Petrel X, which has visited the deepest parts of the ocean and uses a ceramic composite pressure vessel. So if a company were really set on making a carbon fiber composite pressure vessel, they would just have to do a lot more testing and research than OceanGate were ever willing to do. He also pointed out that while acrylic is approved today, when it was first introduced as a window material back 70 odd years ago, it was greeted with the same kind of skepticism and dismissals by armchair engineers who thought that a plastic should not be used in a high pressure, pressure hull material. And Mr. Kemper actually went into a lot of detail about the window which was on the Titan submersible, how it was only rated to 1,000 meters or so, which was far less than the dive depth. Now, lots of people immediately jumped on that fact and assumed that that was the cause of the failure, but the wreckage pattern suggests otherwise. So anyway, rewinding to the 1950s, submersibles would use hard materials like glass, and later they would try sapphire. So this would be placed inside a conical interface where you'd be held in place against the hull using the water pressure. But there was obviously a surface around the outside along the edges of this cone where if water started to creep in and it found a way all the way through, it could actually start either cutting into the steel, or the other problem is that these hard materials, they would tend to fracture when they started to fail, and the fracture could happen so quickly you had no chance of doing anything about it. So instead of going with a stronger material, go with a softer material, and this, as it's squeezed, it tends to distort and fill any gaps. A bit like how a cork can be used to seal a bottle. And lacking the modern computational analysis tools we have, the scientists working on this basically built a rig to test various window shapes under various pressures. And you see on this slide that was presented how some of these pieces of acrylic failed. Using this empirical data, they were able to draw lines on a graph and say, if you're on this side of the line, you're good. If you're on the wrong side of the line, your window doesn't qualify. The problem for OceanGate was that their window wasn't the same shape as the windows which had been tested and validated to destruction. The standard wanted shapes which were spherical on the outside and had an indented sphere on the inside. But OceanGate wanted to have a flat surface on the inside because the optical effect of that concave section would be to make everything outside seem further away. And since you've got tourists on board who wanted to look out that window and see the Titanic up close, you didn't want the window shape to be making it look further away than it actually is. So simply because it wasn't the right shape, it wasn't rated for a human pressure vessel to that depth. And you might then naively think, well, wait a second, if we're having a flat inner surface, we've got more of this acrylic material in there. Surely it should actually be stronger because we've got more material in there. Well, it's not quite as simple as that. Kemper Engineering did some computer analysis of the design, and it's non-trivial because you have the windows sitting inside a structure, and both structures will actually move under the pressure of the water outside. But when they start to take a look at how the stress is redistributed inside this window frame, it showed that all that stress and strain would end up getting concentrated in one corner. And indeed, if you put it side by side with the approved window design, the one that uses less acrylic, it turns out that the loads overall are lower on the spherical design. And it's kind of hard to tell from this, by the way, because they use different color scales on both sides. But point is that including that material to not have that magnification or demagnification effect meant that the peak load on any point in the window was higher on the left one than on the right one. And I found this fascinating because it's a non-obvious, effect. Again, I don't believe that the window was involved in a failure, but this is a fascinating observation about something that's not immediately obvious. So anyway, let's come back to the carbon fiber pressure hull. The new information was all presented by Donald Kramer of the NTSB, and there's 3 documents that he came up with. One was imagery of the wreckage on the seafloor, another was an analysis of wreckage recovered, and the third one was his testimony, which included a slide deck which talked about some specific details. And we're going to start with his discussion of the fabrication of the hull, because that will let you understand some of the stuff you see with the destruction of the hull. So there was the V1 hull, which was mentioned, manufactured in 2017. It didn't perform as expected, and so they decided to build the V2 hull. There was also the 1/3 scale demonstrator, which, again, didn't perform as expected. Now, these were all largely built the same way. You take a big steel mandrel, and you start wrapping carbon fiber composite around it. Now, for some layers, they run the carbon fiber circumferentially, like as if they're rotating it. In the other cases, they'll run back and forth. That will be longitudinals. And for the ultimate design they used, they would do 2 circumferential layers and then 1 longitudinal layer. This is, of course, important because it's stronger along the direction that you're laying it up. And by the way, Boeing, which they consulted with, wanted to also have 45-degree layers, and I presume that that was actually more difficult than the fabricator could manage, so they didn't do that. One of the problems they had with fabrication at all scales was they would form these wrinkles in the surface, and once you had a small deviation from circularity, it would apparently build up and get to a thicker and thicker wrinkle. And when you have the carbon fiber filaments changing direction, that weakens the structure. So they believed that getting rid of the wrinkles or reducing or controlling them would be important to making sure the structure was strong. So yeah, this image shows the wrinkle getting worse as it gets laid thicker and thicker. So what they thought was, hey, let's just lay down a short layer and then machine the surface flat again and then start laying another layer of carbon fiber around it. So instead of making one 5-inch thick cylinder, they made 5 1-inch thick cylinders on top of each other. So they'd lay down 133 layers and then they would cure that in the oven. But to make it sticky with its neighbouring layers, they wanted to make sure the outer surface was still rough and activated. So what you do is you wrap it in a material called a peel ply, and that leaves an impression in the surface, and also it sort of chemically activates the surface to be more receptive to glue. So after that's cured in the oven, take it out, machine it down to a perfect cylinder again, lay on the glue, and then on top of that you start putting in your next layer of carbon fiber, 133 layers, and you repeat that until you get 5 layers thick. And so yeah, here's an example showing it. And by the way, it's slightly thicker than 5 inches because those adhesive layers add a little extra to the thickness. And here's a close-up showing how one of those wrinkles is being ground down and then it's flat going outwards. But it wasn't 100% successful at this because what they did was they took an end section and they counted the number of wrinkles in each layer. They found out that with each layer, they got more and more wrinkles. So it wasn't perfectly circular sufficiently to remove the wrinkling problem. But I guess what they're thinking is that the reduction in the wrinkles in the outer layers helped with the strength of those layers, even although cutting out or grinding out those wrinkles probably weakened the layers below a little. And also, since the peel ply was removed, that made that spot a little less sticky. So now, knowing about this multi-layer construction, let's look at the destruction. And there's this section that's labelled Hull Piece A. It was the biggest, longest piece of carbon fiber composite that was recovered. And it split into multiple layers that are 1 or 2 inches thick. And in fact, it's split along those lines, those layers, where they did the peel ply and then the green glue that was used. And so while you're looking at these photos, there's a sort of color coding you can use. The raw carbon fiber composite is black. The glue between the layers is green. There's a grey outer layer, that's the truck bed liner they used to seal it from the elements. And then the interior was painted white. And so you can see all those colors in this shot. So yeah, they did actually pull this wreckage apart because they were obviously trying to recover the human remains. And this was placed out on the seabed and then later returned so that they could actually look at it up close in a lab. It was split by layer 1, which was the innermost layer. Then layer 2 and 3 was the next section. And then layers 4 and 5, the outer section, were split separately. I don't know if that tells us anything about the curing, say, between layer 2 and 3 was better than the layer between 1 and 2. But it seems reasonable to me to think that the glue that held the layers together was likely not as strong as the cured resin which held together the carbon fiber sections. For this hull to avoid buckling, those layers have to not slide as pressure is applied to it. So a large piece was recovered and it was dissected and analysed in various ways to measure the quality. For example, here's a gorgeous, high-quality microscopic image showing the adhesive between the two layers. This looks like a pretty good join and it didn't break during the event. But here's another section from which had actually separated. And you can see a whole lot of stuff going on here.
So in some areas you can see the checkerboard pattern where this peel ply was laid down and it roughed up the surface. Underneath that though, sometimes it tore off and you can see just the carbon fiber that's running vertically along this image. In other areas, the glue is still sitting up high, and that section is where the glue tore away from the outer shell during the collapse. Another interesting observation is if there was any underlying weave or imperfection, then that would translate directly to different thicknesses of adhesive going outwards, or it might even create voids. And so they found thin layers associated with this. They found voids, but they also found periodic sections where you would have glue on one area, black carbon fiber on the next one, in patterns that were sort of predictable over large areas. And then in some areas, they found the peel ply imprint with a cream-coloured powder that was embedded into the grooves. They wanted to know what this material was, so they essentially scraped it out of there, got enough of a sample that they could put it into a spectrometer and take a look at the chemical composition, and it turned out that it pretty much matched the chemical composition of the glue. So it looks like this glue has been crushed to a powder. There's also evidence of rubbing marks along the longitudinal axis. So this is a microscopic examination. What this is showing us is between these glued layers, there was sometimes motion, enough to crush and you grind the glue into a powder. And that is really not a good sign. The strength of this hull, its ability to resist buckling under outside pressure, is dependent upon these layers not to slide over each other. Now, if you think about it, if you have like a bunch of sheets of paper and you roll it into a cylinder, the sheets of paper slide over each other. If you glue those pages together, it's harder to roll it into a cylinder because of the interply motion is eliminated. Granted, it's more like 133 layers strongly bonded together and then one weak bond and then another 133 layers. But point is, that's another weak point which I hadn't really been aware of. Now, on top of this, they were also able to look at the quality of the bonding between successive layers of the carbon fiber composite. What they did was they took a slice and you do an oblique cut through it, so it's slowly descending through the layers. And then at each layer, the voids become very obvious. When you look at this section underneath a microscope, you can see that the top layer of the fibers are running vertically, but in each of these voids that's outlined, you can look down underneath to the fibers that are running horizontally, right? So these are a change in the wrapping or the laydown of the fibers. And look, I'm going to be honest here, I'm not an engineer. I don't know enough about thick carbon fiber composites to know whether this is just meh, it's bad, or it is horrific. Okay, so coming back out of the microscopic view to the macroscopic view, this is the video that I used in the previous discussion where I said that I believed that the failure had started at the forward ring on account of the majority of the debris being pushed into the rear. I'm actually willing to say that I may not be correct on that, because really what I'm saying is that the water ingress started at the front, at that forward ring. The actual collapse may have started elsewhere, propagated to the front where the water started coming in. Now, we didn't see that front ring in any of these videos, but now NTSB has given us some imagery of the rings that were discovered. There is actually a debris map, but the names don't actually make that much sense to me. I'm thinking this was about 30 meters away from the main wreck. It was pushed further forwards by the looks of things. So the way it's facing, the forward side is up, that's where the dome would be. What we were interested in seeing was the other side, the C channel where the carbon fiber hull was connected, and we got that image. So yeah, first thing to notice is there should be a flange running around the inside and the outside, while the outside one still has sections attached. The inside one is completely gone. Also, there's almost no evidence of the glue that was in there holding the carbon fiber on. And to be fair, this was a surface which was machined clean when it was reused, so it was probably quite a smooth surface compared to the carbon fiber composite that was on the other side. So you would naturally expect the glue to stick to that instead. And indeed, if you look at the long piece that was recovered, on the front end you see where it says A layers 4 and 5. That's white glue that is in there that has remained attached. This piece ran the entire length right up into that channel on the titanium ring. You get a better look at it here. You can see that in places it's detached from the carbon fiber, other places it's pulled away from the titanium, but it's also split in the middle of the glue. The glue is undeniably a weak point in this particular design. Although it is worth noting, if you look at piece A, by the way, while it has a clean surface at one end, at the aft end, it is a break, so it wasn't a perfect long segment of this of the sub. Anyway, there's a close-up image of the C channel, and again, it shows no adhesive in there. What I find most interesting is that the outer flange has been bent and broken off that way, whereas the inner channel, it has sheared off. There's a shear fracture all the way around. And that's kind of what you would expect if you've got a lot of water pressure pushing the hull in all around. And so yeah, while that long piece A was right up against it and didn't break, it was definitely pushed through that titanium flange hard enough to shear it off. So while it wasn't broken as much as the other pieces of carbon fiber in the hull, it was still subject to some very powerful forces during the collapse. Another thing worth mentioning is that because this 5-layer hull was thicker than the original design, it was actually too thick to go into that C channel, so they had to machine material off around the front. And I think if you look at this, you can see the ridge around the top where they've had to machine that down. And you can also see it in some of the images of the material on the ocean floor. But hey, we're only getting rid of a small amount of carbon fiber, and we're replacing it with titanium, which is so much better, right? That couldn't possibly be a problem, right? So how does the forward ring compare to the rear ring? Well, it was still attached to the aft hemisphere. There were actually bolts that were still secured. But yeah, this was recovered, and if you look at the C channel, there was actually a section where glue still remained. And this is actually visible in some of the wreckage photos that have been published, if you see down the bottom there. Note, by the way, that it is very close to that long, large section of the hull. That to me says that the section where the glue remains probably was subject to less forces. Interestingly, you can also see impressions of the carbon fibers laminations that were cast into the glue structure, and you can also see evidence of wrinkles that have been fixed and ground away. So now that long piece, that was at the top of the vehicle. The material that was towards the bottom, that has been broken into smaller pieces. That tells me that the failure probably started on the bottom, it probably started near the front, and then water started ingressing there, shearing off everything, and that was the end of the day. The glue has often been cited as a potential weak point, but I think its main role might be that it had two surfaces that might move at different rates, and if one small part of the hull moved just a little as it relaxed under pressure, it would be like a small energy release which could then translate to bigger and bigger failures and eventually the collapse. One other hull piece that's worth mentioning is piece D. It was one from which they actually observed a bend, right? A buckle in the structure rather than simply broken. A cylindrical structure beginning to buckle under exterior pressure is essentially unstable and will very quickly lose its integrity and collapse completely. Now, it looks to me like the forward end of this is machined and there may be traces of that glue from the forward ring. The NTSB hasn't specifically established this, but that's what it looks like to me. Again, we may find out more when the NTSB publish their full report. This section that buckled, incidentally, is from the top right, assuming you're facing forwards. Anyway, finally, I want to move on to the metaphorical bombshell that the NTSB dude dropped on the real-time monitoring system, the much vaunted real-time monitoring system, which was supposed to have detected this and made them stop before they descended into disaster. Now, we had the designer of that system give testimony. You can go and watch that if you want. But the basic idea is there's two types of sensors. The acoustic sensors, which listen for things breaking. When there's an acoustic event, a click or something, then if it exceeded some threshold, they would trigger a count. And if they had too many on a specific dive, then they would decide to surface. So they would see plots like this afterwards showing these little purple lines where there's like acoustic events happening. By the way, it turned out that some of those sensors weren't actually working. Compare channel 1 to channel 2. I think the big problem with this is that they didn't try to localize where the events were coming from because that might have given them some clue of where the problems were. Now, another less well-known part of the system were the strain gauges, which were mounted to the inside surface of the hull. And what would happen is, as the hull changed shape, the distance the electricity had to travel across these would change, and therefore you would measure distortions in the hull, that is, strain. So using these, you would get plots showing the strain on the hull, well, actually technically going down, I think, because it's actually getting squished rather than stretched, and as they reach depth, and then as they come back, you see the hull returning to normal as it ascends towards the surface. Now, there's one particular dive that keeps getting mentioned, Dive 80. It was to the Titanic, and it went fine, but on the way back up, as they were going to about 1,000 meters, there was a big bang. Everyone on board heard it. In fact, people on the surface may have heard it. And in his infinite wisdom, Stockton Rush dismissed this as the hull moving against the exterior structure, steel slipping over the hull and making some noise, which was unrelated to the physical strength of the carbon fiber itself. So now the NTSB dude, knowing what he's doing, put the strain data alongside the acoustic data, and guess what? There is a jump in the strain at that exact moment on one of the sensors. And I think this is the sensor that is in the bottom left, right up against the forward ring. The other thing he realized is that plotting the data versus time doesn't work nearly as well as plotting the data versus depth. So this is the strain gauge that was affected in dive 75. Now fast forward to dive 80 and 81. So the blue data from dive 80 starts out and it follows basically the same slope up and the same slope down. But for the next dive, after that big bang, suddenly the curve changes early on. The way the hull is flexing has changed after that acoustic event on dive 80. And this change is specifically localized to an area which is forward and bottom left on the carbon fiber hull up against that ring. This is seen for the next few dives in both the hoop stress and the longitudinal stress, and this is the last set of dives that they have data for. So I'm thinking that this shows the real-time monitoring system was successful in detecting a failure before it happened. Unfortunately, it was unsuccessful in telling the OceanGate team, and specifically Stockton Rush, who was far too interested in forging ahead rather than asking their engineers to take a closer look at this. Dive 80 was in 2022. They completed a couple of other deep dives and then returned home. The submarine got stored outside, if you remember, before being brought in. There was a couple of cases when they were bringing it out in 2023 where the barge capsized and dumped it into the ocean. It got towed behind a barge on the high seas and no doubt got battered around. All of these things probably contributed in their own way to weakening things. And since I pointed out that the top of the thing seems more intact, here's a hypothetical. One of the engineers expressed concern about lifting the submarine by the two rings. Well, if you think about it, if you're putting the lifting force on those rings, that means the bottom wants to go down. The bottom of the rings are getting pulled away ever so slightly while the top rings are being compressed. Therefore, the bottom of those rings should be slightly weaker than the top. Anyway, at this point, we're now waiting for the NTSB report if we want to get any more clues. One thing I do want to point out, though, that I noticed, is if you look at that dome, there is like a dark brown line, like a ring around it. That is like an impact crater on the ocean floor, if you think about it. The domes and the main structure fell onto the seabed sufficiently fast that they would disrupt it and send out this sort of ring of dark debris which would then resettle. These fell relatively close together because they were heavy, but some of the debris took a little longer to fall and is up to 300 meters away by the looks of things. See, that would be a great little, neat observation if it wasn't for the fact that there are basically dead people in there, or dead bits of people in there. And look, I should also say that, one of the things you shouldn't take away from this is that submersibles are somehow death traps, because we had a number of experts from the submersibles industry that have built great hardware that has been very reliable. They've followed the standards, they've designed the standards. And there's actually a fundamental problem is that there was no legal way for OceanGate to take passengers, even if it had built a properly classed submersible. They had to make this dodge where they were all mission specialists. And perhaps that is a problem that if OceanGate had found a more legal way of doing it, they might have been more inclined to follow the standards and made a safer thing. Now that OceanGate is gone, there's essentially no way for regular people who happen to have too much money to get down to the ocean floor and see sights such as this. What I'm saying is that most of the people on the Titan believed in deep sea tourism, and it would be a shame if it were to end with this. I'm Scott Manley. Fly safe.